Okay, AP Chem. Today we're going to do a review of the things that we learned in the bonding unit. So let's start from the beginning. When we create these drawings that are supposed to represent the molecules, there's a couple things that we need to remember. The first one is the Octet Rule. And the Octet Rule is for most normal compounds. What that means is that atoms gain, lose, or share valence electrons to obtain 8 or a full valence shell and have a noble gas configuration. Ionic bonds are a metal and a nonmetal added together. The valence electrons are transferred, and then crystal lattices are created that are attracted to each other by the electrostatic attraction between the positive cation and the negative anion. A covalent bond is when two nonmetals are together, and that's what we're going to draw the Lewis structures of as these covalent bonds. So in two nonmetals bonding together, valence electrons are shared. A single bond is 2 shared electrons, or 1 pair. A double bond is 4 shared electrons, or 2 pairs. A triple bond is 6 shared electrons, or 3 pairs. So as the number of bonds increases, the distance between the atoms decreases. So that means a single bond is longer than a double bond, and a triple bond is the shortest. Lone pairs of electrons are unshared pairs of electrons as opposed to those shared or bonding pairs of electrons. We cannot forget our diatomic elements, which is our high 7 elements, or hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, and chlorine. So Brinkelhoff or Janine molecules or your high 7, those will form what's called diatomic molecules, meaning they will be covalently bonded together, the pair of atoms. Hydrogen, bromine, fluorine, iodine, and chlorine have single bonds. Those are all dead ends. They tend to form one bond. Oxygen has a double bond, and nitrogen has a triple bond. That's why nitrogen stores so much energy in their bond. So the basic rules for forming Lewis structures is sum up the valence electrons from all the atoms off the periodic table of the elements. Try to pick out which one is the central atom. That's the one that occurs the least often usually. There's lots of other ways you can determine it too. For example, hydrogen and the halogens are on the outside because they form one bond, unless we're in a situation where the octet is being expanded. We want to make sure that we bond them together and keep track of those valence electrons. So the number of valence electrons a structure has is exactly the number of electrons that will be represented in the Lewis structure. No less, no more. Atoms want to have 8 valence electrons. They want to be to the point where they're either sharing or owning 8 electrons, except for hydrogen's only 2. When you're drawing it and you recognize that you do not have enough electrons to satisfy all of the elements, that's when those double and triple bonds come in. So you determine that a double and a triple bond is in play once you decide that you do not have enough electrons to satisfy all the elements. So we check. Each atom should have a full octet, except for hydrogen can only hold 2 electrons. And then there's a couple exceptions, like boron has to be satisfied without a full octet. You usually get 6. So halogens are usually bonded to only one other atom. Carbon, oxygen, nitrogen, and sulfur are notorious for forming multiple bonds. And remember, we talked about that bond dissociation energy, or the total energy that is in those bonds. You have to add energy to break bonds, and you get energy back when you make new bonds. High bond dissociation energy usually means the chemical is unreactive because it takes a lot of energy to break it down. So a good example is that nitrogen-nitrogen triple bond. That stores a lot of energy. We know that nitrogen is completely inert, but when you do break those bonds, such as in TNT, when you can break those nitrogen triple bonds, a lot of energy is involved. So Vesper is that valence shell electron pair repulsion, and this is going to help us determine what the shape of a molecule would be. So remember we went through that boron has 3 bonds, but it lies flat, so it is trigonal planar. Carbon forms 4 bonds, so it is tetrahedral. Nitrogen usually forms 3 bonds, but it has a lone pair of electrons. That's that valence shell electron pair repulsion. Those lone pairs of electrons take up just as much, as a matter of fact, a little bit more space than a bonding pair. So nitrogen's family usually forms what's called trigonal pyramidal. Oxygen usually forms 2 bonds, has 6 electrons, and it has 2 lone pairs of electrons that take up as much space as the bonding pairs of electrons. So oxygen will usually form a bent shape. And fluorine, or all the halogens, they form linear molecules because they only form 1 bond. So then we can determine bond angles. All of the bond angles are going to be very similar. The tetrahedral for carbon is going to be a 109.5. Then nitrogen is a little bit less than that, about 107, because that lone pair of electrons warps the bond down. Oxygen has 2 lone pairs of electrons warping the bond down, so the angle there is about 105. That's not something that we typically focus on. Resonance is a phenomenon when more than one electron dot structure represents the bonding pattern of a molecule. So for example, if you have a molecule that has 1 single bond and 1 double bond, but they're both between oxygens, typically the real structure will be somewhere in between, like each will get 1.5 bonds instead of 1 oxygen getting a single bond and 1 oxygen getting a double bond. There are a couple exceptions to this octet rule. Nitrogen's notorious for that, forms some with an odd number of electrons. There's also situations where we can exceed the octet rule, and this only happens when the central atom has access to a D sublevel. So can't be anything in the first or second principal energy level. So this only starts with nonmetals starting in the 3rd principal energy level. So sulfur would be one example of that, or phosphorus. There's also boron that forms less than an octet, only 6 valence electrons, because he has 3. He can share those 3, but he can't just take random electrons from other people. Now, there's also a concept called polarity. Polarity is a difference in electronegativity. The more electronegative an element it is, the more likely it is to have a greater share of the electrons, therefore be partially negative. Now remember, fluorine is the most electronegative on the periodic table of the elements. Oxygen's next, and chlorine and nitrogen. So the closer you are to fluorine, the more electronegative you are. The only truly non-electronegative or non-polar molecules are diatomic elements. So you can use electronegativity to predict what type of bond 2 atoms will have, whether it's going to be ionic, polar covalent, or non-polar covalent. So very small differences in electronegativity result in a non-polar covalent bond. Middle is polar covalent bond, and greater than 2 is ionic. That's when the electrons are actually transferred. So non-polar covalent bonds are equal sharing of electrons. Polar covalent bonds are unequal sharing of electrons, and ionic bonds are transfer of electrons. So what does that mean? When you have a polar bond, one atom pulls on the electrons with more energy, so therefore it becomes partially negative. So the more electronegative an element is, the more it will pull on the shared electrons and the more polar the molecule will be. A good example is HF. There's a huge difference in electronegativity, so that is a very polar covalent molecule. Chlorine, which is Cl2, completely the same electronegativity. Therefore, it is a totally nonpolar bond. So molecules can contain polar bonds but be nonpolar overall if they have something called symmetry. They can only have symmetry if they do not have any lone pairs. If there's a lone pair of electrons on the central atom, then you cannot have symmetry. You have to have, for example, CO2 is carbon in the center, double bonded to two oxygens. There's no lone pairs on the central atom carbon, so therefore this is an example of symmetry. CH4 is notoriously symmetrical and will be nonpolar because of symmetry. CO2, notoriously symmetrical, so nonpolar, any polarity is canceled out by symmetry. So like dissolves like, remember that we did activities together. Polar substances only mix with other polar substances. Nonpolar substances only mix with other nonpolar substances. So when you are classifying, you would go down and you say, well, sodium and fluorine has a large electronegativity difference, so it is ionic. Carbon and hydrogen has an electronegativity difference of 0.4, so we classify that as nonpolar. Sodium chloride is ionic. Oxygen to oxygen is a nonpolar covalent bond. And bromine to hydrogen would be a polar covalent bond. So there's some examples of the different types of bonds. Here's a picture of resonance structures. So when you are calculating and deciding what the Lewis dot diagram would be for SO3, you would notice that you're going to have 4 bonds. So one oxygen would have a double bond and the other 2 have a single bond. But the real structure is somewhere between all of that. And the reason we know that is because we can measure the bond energy and the bond length, and they're all going to measure out to be the same. And that's because of resonance. The same thing for the carbonate ion. So when we're drawing structures for polyatomic ions, remember that when you're drawing a structure, you count up the number of valence electrons. You're going to do the same thing for polyatomic ions, except for the fact that that -2 means that I have 2 extra electrons hanging around that I've taken from somebody else. So this resonance structure for CO3, 2-, or the carbonate ion, would have 4 valence electrons from carbon. It would have 3 times 6 from oxygen. So 18 plus 4, 22. But then you have the extra 2 electrons. So you have 24 electrons total that you need to represent. You would recognize you would need 1 double bond, but the real Lewis structure is going to be somewhere between all of those. We also went in great detail about the difference between intermolecular forces and intramolecular forces. Inter is between 2 different molecules. Intra is inside molecules. That's what keeps the atoms in a compound stuck to each other. Those are the chemical bonds. The intramolecular forces are polar covalent, nonpolar covalent. Those are always greater, always more energy than the intermolecular forces. The intermolecular forces can be determined by the type of bonds the molecule has. So dipole-dipole forces occurs when you have polar covalent molecules next to each other. It doesn't have to be the same polar covalent molecule. A special kind of dipole-dipole is hydrogen bonding. Remember, hydrogen bonding is fun, F-O-N. So it is nitrogen, oxygen, or fluorine bonded to hydrogens. If there's no either HN, HO, or HF bonds, there's no hydrogen bonding. And remember, our weakest one is the London dispersion forces. Those are the weakest. So you've kind of got 3 there that you need to kind of keep track of and determine what is in play. So how do I determine which one it is? Well, you're going to draw the Lewis structure for the molecule. See if the structure has hydrogen bonding. If it doesn't have hydrogen bonding, then you're going to check and see Is the molecule polar? If the molecule's polar, there's going to be different atoms involved in the covalent bond, and then it would have dipole-dipole forces. Remember that all molecules have London dispersion forces, but nonpolar molecules are the only ones who only have London dispersion forces. There's a summary of our bonding unit.